Our last section, we're going to look at area and arc length in polar form. All right, remember back to the good old days in Calc 1? If I gave you some function f of x like so, and I gave you an a value, and I gave you a b value, and I asked you to find this area under this curve bounded by the axis, how did you do that? Turned out that the area was the integral from a to b of f of x dx. And how did we determine that that really should be the area? How did we derive that formula? Anybody remember? We used Riemann sums. So what you're saying is, what we did is we built rectangles in here, didn't we? Like so. And how wide was each rectangle? Delta x, it was the width of the rectangle. And how tall was each rectangle? The height of the function. So what we saw is we could find an approximation for the area by adding up the area of each rectangle. So this summation would mean for rectangle number 1, I find its height, I find its width. For rectangle number 2, I find its height, its width, so on and so forth, and then I add them all up. And then we showed that the exact area was the limit as n went to infinity, the sum from I equals 1 to n of f of x sub I delta x, which we defined as the definite integral. So, when we work in rectangular form, we develop our formula for area by building rectangles. What do we do in polar form? So let's say I have some curve. I don't know, polar curves are kind of weird sometimes. Looks something like that maybe. So this is some curve r equals some function involving theta. Is it going to make sense to build rectangles? Not in polar form. So what do we build? Circles. Well, not quite circles, but you're on the right track. What we're going to do, instead of building a rectangle, we're going to build a teeny tiny little sector of a circle. And we're going to find the area of that teeny tiny little sector of a circle, and then we'll add up all the areas, and then we'll take more and more and more of them, which means we'll eventually integrate. So does anybody remember how to find what the formula is for the area of a sector of a circle? No, I didn't expect you to remember that. So the area of a sector is 1/2 times the radius squared times theta. So we would have the area of the entire region is approximately the sum from I equals 1 to n of 1/2 times the radius squared. Now, again, think we're building teeny tiny little sectors here, just a very, very small angle. If we have just a very, very small angle, what are we going to call that angle? Kind of like when we built a really, really skinny rectangle. What did we call the width? We called it dx for a rectangle. When we're building a teeny tiny little sector, it's going to be delta theta. So how are we going to find the exact area? We'll take the limit as n goes to infinity, and then the limit as the n goes to infinity of this formula is exactly the same as an integral. So our formula for area in polar form is going to be 1/2 the integral from theta 1 to theta 2, these will be angles here, of r squared d theta. Questions on that?
So even if it's not a truly smooth circle or anything like that, it can have jagged edges.
Yep. Just like this, remember when we built our rectangle, we chose one side or the other to define our height? But eventually our rectangles got so skinny that these two heights were so close to each other that it really didn't matter. You're going to have the same deal here. You're going to pick one of these sides to build your radius. It really doesn't matter which one. And then when your angle is small enough, these two lengths are so close to being practically the same that we call them the same. So you make your angle small enough, these radii are, for all intent and purposes, exactly the same. But then that goes to 0 in the difference of them.
What's theta 1 and theta 2?
Theta 1 and theta 2 will be your starting angle and your ending angle. For example, if I wanted this area, then I would start at angle 0, and I would end at angle pi over 2. Just like in rectangular form, we went from there to there, so we went from a to b on our integral.
It always works counterclockwise, right?
Truthfully, it doesn't matter. We will always set them up counterclockwise, because if we set them up counterclockwise, that means we'll have the smaller number on bottom and the bigger number on top. What if we have them the other way? What if the big number's on bottom and the small number's on top? You can flip them, and the penalty is putting a negative sign out front of here. So we'll always set it up counterclockwise, just so we always have small and big. But you could do it either way.
Is it the same where stuff below the horizontal axis would be negative?
No. Here, we're just finding the true area, so we're not considering area down here to be negative. Let's start with something easy like a circle. We'll find the area of a circle, and it'll just give us the whole positive answer. All right, so let's do an example. Let's start with a circle. Somebody give me the equation of a circle in polar form. R equals 3 is a circle. That's a wonderful circle because it has center at the origin. Nice, easy circle to find its area. So, we know what the area should be. This is a circle with center at the origin, radius of 3. What's the area of a circle with radius 3? Should be 9 pi, correct? Okay. So, according to our answer, area should be 1/2 the integral of r squared d theta. That's 1/2 the integral of 9d theta. What are my bounds of integration?
0 to 2 pi.
0 to 2 pi should certainly work. Why 0 to 2 pi?
So full rotation.
It's all the way around the circle, isn't it? Or I could have chosen to go 0 to pi and only do half the circle, and then I would just have to
Get rid of the 1/2.
get rid of the 1/2, double my answer. All right. What's the antiderivative of 9?
9 theta.
9 theta. So we're going to have 1/2 times 9 theta, and we've got to plug in 0 and 2 pi. When I plug in 2 pi, I get 18 pi divided by 2, that's 9 pi, minus when I plug in 0, I get 0. Did we get the right answer? We sure did, because the answer should have been pi r squared. We got pi r squared. All right, let's try a harder one. How about the interior of r equals 6 sine theta? What I find very helpful on these is to grab my calculator and draw a graph. Mode. I'm in polar form, that's good. Y equals 6 sine theta. Graph that. Might have to zoom out a little bit. What's that the shape of? It's once again a circle. Doesn't quite look like a circle. And again, the reason it doesn't look like a circle is the distance of the tick marks on the x-axis and the distance between the tick marks on the y-axis aren't exactly the same. There's a way to fix that. Anybody know how to make the tick marks on your calculator the same? Zoom. Square. Still doesn't look like a circle. Well, it doesn't matter if it's a circle or not. How do we find its area? We're going to have area is 1/2 the integral of the radius, that's 6 sine theta squared d theta. What do we use for theta values this time?
We go 0 to 6.
0 to pi? Okay, so what I like to do, if I think I should go 0 to pi, I like to set up my window to go 0 to pi and then see what I get. If my window goes 0 to pi, it does look like I get the whole circle, doesn't it? Zero. What if I go 0 to pi over 2? Do I still get the whole circle? No, I only get half the circle. So again, I could go 0 to pi. That appears to give me the full circle. Or I could go 0 to pi over 2 and then just double my answer.
You get a different answer if you went 0 to 2 pi?
Yes. How come? I think what it's doing if you go between 0 and 2 pi, I think it draws it twice. For example, let's change our window to go from pi to 2 pi. So notice when you go pi to 2 pi, it draws it again. So if you go 0 to 2 pi, you're actually going around twice. Your answer is going to be twice as big as it should be. So you do need to be careful on those. All right, well that's going to be 6 squared is 36. 36 times a half is 18. The integral from 0 to pi of sine squared theta d theta. How do you find the antiderivative of sine squared theta d theta? So this is a good review of this previous material portion. How do you integrate sine squared theta? All right, when you have sines and cosines, you hope one of them has an odd power. If one of them has an odd power, then you save that and you let u be the other thing. And then du will work out to be that. What do you do if both sine and cosine, in this case only sine, has just even powers?
Use one of the identities.
Which identity?
Power reduction.
The power reduction identity. So this is going to be 18, the integral from 0 to pi of 1/2 times 1 minus cosine 2 theta. D theta, that's the power reduction formula for sine squared. I'm going to take this 1/2 and I'm going to move it outside. 1/2 times 18 is 9 times the integral of 1 theta minus the integral of cosine 2 theta. That would be the derivative. I want the antiderivative. 1/2 sine of 2 theta. Remember, the integral of cosine is positive sine, but we already have this negative in front, so it does stay negative. Evaluate at 0 and pi. I plug pi in, I get 9 pi, and then when I plug 0 in, sine of 2 pi is, or when I plug pi in, I mean, sine of 2 pi is 0. So that's just going to be 9 pi minus, when I plug 0 in, I get 0 there. I get sine of 0. Sine of 0 is 0. So when I plug 0 in, I get 0 for the whole thing. So it looks like my final answer is 9 pi. Questions on that? Pretty sure that's the right answer. Because look at that picture. What is that?
Circles.
It's a circle. What's its radius? And well, if you count, if you go here and count up, it looks like, well, I got to go back to zoom 6 so I can. Looks like there are 1, 2, 3, 4, 5, 6 little tick marks. So it looks like the radius is 3. That's another circle of radius 3. Its area should be pi r squared. Pi times r squared. All right, let's try one that's not a circle. How about 1 petal of r equals 4 sine of 3 theta. All right, so again, I like to draw a picture. Y equals 4 sine 3 theta. And I'm going to go back to zoom 6. So it will start by going from 0 to 2 pi. So I want 1 petal. Does it matter which one I pick? No, not at all. My answer is fairly simple. My answer is the area. Most of it's fairly simple. 1/2 the integral of my radius squared, so that's going to be 16 sine squared 3 theta d theta. The only question is, what should my bounds of integration be so that I only get 1 petal?
0 to pi.
0 to what?
Pi halves.
0 to pi halves. All right, let's try that. 0 to pi over 2. If I go 0 to pi over 2, it draws more than 1 petal.
So you pi thirds.
Pi thirds. 0 to pi over 3. That does look like it draws 1 complete petal. All right, so how do I figure that out without just pushing buttons on my calculator and guessing and hoping that eventually I get the right answer?
There's 3 petals to start with, so taking 1/3 of the whole thing.
You could take 1/3 of the whole thing, but even there you have to be careful what values of theta from 0 to what draws the whole thing. I don't think it's 0 to 2 pi. I think 0 to 2 pi draws the whole thing twice.
0 to pi.
0 to pi, I think, is what you would need. All right, so here's what I like to do. I noticed, I watch very carefully when it graphs. So you got to watch because it happens fast. Zoom 6. I noticed it started right here. It started right here at the origin. And it drew 1 petal by coming around and hitting the origin again. In other words, I want 4 sine of 3 theta to be 0. Because to hit the origin, that means your radius has to be 0. So what values of theta can I plug in to make 4 sine of 3 theta equal to 0? Well, I can certainly plug in 0. What else? Pi over 3 would work. Why pi over 3? That would result in pi. So what you need to remember is, when does sine of something equal 0? 3 theta could be 0, could be pi, could be 2 pi, could be 3 pi, dot, 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 etc., etc. So if I divide by 3, that tells me theta should be 0, pi over 3, 2 pi over 3, pi, dot, dot, dot. So I think it's going to hit from 0 to pi over 3 is going to make one loop. From pi over 3 to 2 pi over 3 is going to make the second loop. And from pi over 3 to pi is going to make the third loop. And then after that, it just keeps cycling around on itself over and over again. So I think I want to make my bounds go 0 to pi over 3. Truth is, I could use any of those. I could use 0 to pi over 3. I could use pi over 3 to 2 pi over 3. I could use pi over 3 to pi. But I really like using 0 when I can. Why do I really like using 0? Makes it real easy to plug in. I like plugging in 0. How do you integrate that?
Same what it is last time.
Same as last time. You're going to have to use the half angle formula. So you're going to have a half times 16, that's 8, times the integral of 1/2 times 1 minus cosine of 6 theta. Because every time you use the half angle identity, every time you use the power reduction identity, it doubles the angle. So we started at a 3 theta, it doubles to a 6 theta. So you're going to use that power reduction formula a lot in this section to evaluate these integrals. 8 times 1/2 is 4. Times, I integrate, I get theta minus 1/6 sine theta. Sine 6 theta, I'm sorry. And then I got to plug in 0 and pi over 3. So that's 4 times pi over 3 minus 1/6 times, what's the sine of, well, I plug pi over 3 in. 6 times pi over 3 is 2 pi. What's the sine of 2 pi? 0. Minus, when I plug in 0, I'm going to get 0 everywhere again. So it looks like my answer is 4 pi over 3. Questions on that? How about,
Break that answer in radians. And is that a numerical value too? For area? And you put in 3.14, then that's actual, if you were to do addition. Okay.
yeah, that's the beauty of radians. The beauty of radians is the angle measure and the numeric value are exactly the same. That's why things work better in radians than they do degrees. So it looks like a radian answer. It's really just a number. 4 pi over 3, whatever that number is.
So would the area of the whole thing be 4 pi since it's 3 loops?
The area of all 3 loops together would be 4 pi. That's correct. All 3 loops. Multiply by 3. Triplet. All right, how about, that was a good one. How about the inner loop of r equals 2 minus 4 cosine theta? Once again, in theory, the answer is very easy. The area is 1/2 the integral of the radius, 2 minus 4 cosine theta, squared d theta. Once again, the hard part is determining what values do I use for theta. Alright, so I go to my calculator and I draw myself a picture. 2 minus 4 cosine theta. And again, I'm going to watch carefully to see how it's drawn. Graph. Okay, so there's that inner loop that I'm looking for. So I want the area of just that inner loop. Let's draw it again. If you just change something and hit graph again. So how did the calculator draw that? It started right there, didn't it? And drew the bottom part of that inner loop. Let's watch that again. Change something. I wish I could slow it down. Did you see it started right there and drew the bottom half of the inner loop? And then it did the big part, and then it did the top half of the inner loop. So it looks to me as though we could integrate from 0 to something and get the bottom half of that inner loop and then just double the whole answer. So I'm going to start at 0 and I'm going to double my whole answer. Big question is, where do I stop? Well, again, where did that inner loop stop drawing? It stopped drawing right at the lower half of that inner loop stopped right at the origin, which means I need this equation, 2 minus 4 cosine theta, to be 0. That's when it hits the origin, when the radius is 0. That's the same as saying cosine theta is a half. So theta is cosine of what gives a half? Pi over 3. All right, so now I'm just going to use my calculator to check. Window, I want to start at 0, and I want to go to pi, oops, not e, pi over 3, and I want to see if that draws just the bottom half of that inner loop for me. It looks right. It looked like it drew just the bottom half of that inner loop. So I think that's what I want to use for my bounds, 0 to pi over 3. Questions on that? Questions on how I got those bounds? That's the hardest part of these problems, is figuring out what the bounds should be. All right. So that means 2 times a half is 1. I have the integral from 0 to pi over 3. I'm going to take this and I'm going to do a little expansion here. That's going to be 4 minus 4 times 2 is 8. 8 doubled is 16 cosine theta plus 16 cosine squared theta d theta. Well, I can integrate 4, that's not a problem. I can integrate 16 cosine theta, that's not a problem. How do I integrate 16 cosine squared theta? Power reduction formula again. So this is going to be integral from 0 to pi over 3 of 4 minus 16 cosine theta plus 1/2 times 16 times 1 plus cosine of 2 theta. So the power reduction formula, you get a 1/2 out front. For cosine, you get 1 plus cosine, you double your angle. Since that's a theta, we double it to a 2 theta. All right, now I can integrate. 4 theta minus 16 sine theta plus 8 times theta plus 1/2 sine 2 theta, and then I got to plug in my numbers, 0 and pi over 3. I plug in pi over 3, I get 4 pi over 3. minus 16 times. What's the sign of pi over 3? Square root of 3 over 2? Plus 8 pi over 3 plus 8 times a half is 4. I plugged in pi over 3. I had the sine of 2 pi over 3. What's the sine of 2 pi over 3? Pi over 3 is in which quadrant? Or, I'm sorry, 2 pi over 3 is in which quadrant? Not 3. 2. Because 2 pi over 3 is a little bit smaller than 3 pi over 3. And 3 pi over 3 would be back to the axis. So 2 pi over 3 is in quadrant 2. Sine is positive in quadrant 2. The reference angle for 2 pi over 3 is pi over 3. So it's square root of 3 over 2 again. So it looks like my final answer is 4 pi over 3 plus 8 pi over 3 is 12 pi over 3. So that's 4 pi. And then I have minus 8 square roots of 3 plus 2 square roots of 3. So that looks like it's minus 6 square roots of 3. Questions on that?
Why did we get rid of the 1/2 in the beginning? Times the 2, the first step.
Because by going from 0 to pi over 3, I only found the bottom half of the inner loop.
Oh.
So I needed to double it to get the total answer. That's all. So that's why we multiplied by 2 way back at the beginning.
How did you know that the top was the same as the bottom?
How do I know the top is the same as the bottom? Well, I suppose technically I don't. But I think by looking at the graph, you would be pretty convinced that there's symmetry there. And I guess you'll just have to believe me when I say it really is symmetric. The top and the bottom half are exactly the same size. That happens with many, many, many of these polar graphs. If you look at them and they look like they're symmetric, they probably really are. Other questions? All right, let's try one more. How about between the loops? Of r equals 3 minus 6 sine theta. Three minus 6 sine theta, zoom 6. Okay, so what does it mean when it says between the loops?
Subtract the area of the little one and the area of the big one.
Correct. What I want is I want the area inside the big one, but outside the little one. So I think the best way to do that is to find the area of the big one, then find the area of the little one, and subtract my two answers. All right, so my answer is going to be area is 1/2 the integral of 3 minus 6 sine theta all squared d theta minus 1/2 the integral of 3 minus 6 sine theta squared d theta, which is kind of interesting because for the big loop and the small loop you use exactly the same functions. So what's going to make a difference? How are we going to get the big loop and the small loop?
The bounds.
The bounds. Okay. So now we need to figure out how do we get the calculator to draw just the big loop, and how do we get it to draw just the little loop? All right, so again, I'm going to watch it graph here. I'm just going to change one of the numbers, then change it back. I'm going to watch carefully. Okay, so what I notice is it started here. It came in, hit the origin, and drew the little loop. And then after it drew the little loop, it went out and it drew the rest of the big loop. So let's figure out how it drew the little loop first. So it started here, eventually it hit the origin, drew the little loop by coming back to the origin. So it seems like to find where it drew the little loop, I want to take 3 minus 6 sine theta and set that equal to 0. Because it looked like it started the little loop when it hit the origin and it ended the little loop when it hit the origin. That's the same as sine of theta is a half. Which means theta could be, you look on that fancy chart that you've memorized, sine of what gives you a half? Pi over 6? Pi over 6? Okay. And then, when would it hit the origin again? I would need the angle in quadrant number 2. What angle in quadrant number 2? 5 pi over 6. Alright, so let's check. Go to my window. I'm going to type in pi over 6. And then I'm going to type in 5 pi over 6. And that does indeed look like it drew just the little loop for me. So that's the bounds for my second equation, or my second integral, I mean. Pi over 6 and 5 pi over 6. That will make it draw the little loop. Now, how am I going to draw the big loop? Well, let's go back to Zoom 6. So again, it started over here. It came around, drew the little loop, and then went out and completed the big loop. So I think a clever idea would be what? Anybody have a clever idea? What's that? I wouldn't use two integrals. I could, but I'm not going to. I could do one integral that starts at 0 and goes to pi over 6. That would give me that part. And then I could go from 5 pi over 6 all the way around to 2 pi to get the rest of it. So I could use two integrals. That would work. I think there's a better way. Do half of it and multiply by 2. So I think I'm going to do this part, which I know starts at 5 pi over 6, and come around to where it ends right there. So I think that's what I would do, is I would start at 5 pi over 6. I'm going to double that first integral because I'm only going to find half of it. Now the question is, where does it end?
Why couldn't we go just one integral all the way back to the origin?
I suppose you could do that too. You could start at 5 pi over 6 and come all the way around till you hit the origin again. What angle would work to hit the origin? I think it would be 2 pi plus pi over 6. That would work, I think. Let's try it. So we're going to start at 5 pi over 6, and we're going to end at 2 pi plus, oops, wrong button, 2 pi plus pi over 6. That does look like it drew just the outside. So that would work, okay. So then we don't have to double it, do we? So let's see, 2 pi plus pi over 6. 2 pi is 12 pi over 6, plus another pi over 6 would be 13 pi over 6. So those are bounds that would work. I'm not going to work the rest of this one out. Same deal as before, though. You expand this. You're going to have to use your double angle formula, or your power reduction formula, I mean. You're going to have to expand that one. You're going to have to use your half angle, or your power reduction formula. Plug in all your numbers, it'll work. Nick?
The way that you were going to do it originally, where you doubled that, how would you get that bottom?
That's an excellent question.
3 pi over 2, right?
What's that?
3 pi over 2.
3 pi over 2, let's look. So I was going to go from 5 pi over 6. I'm being told 3 pi over 2. And why did you think 3 pi over 2?
I don't remember.
Well, if I go from here and come around and stop right there, isn't that 3 pi over 2?
Oh, yeah, that's why.
That's 3 pi over 2. So I think that would have worked also. I think I could have gone from 5 pi over 6 to 3 pi over 2 and then doubled my answer. I think that would have worked. Other questions?
Can you plug these into your calculator and check this out?
Absolutely, you could take this integral, kind of a pain in the neck even to type it into your calculator, especially if you have the old operating system, but absolutely you could.
Does it need to be in full form?
No, because your calculator just treats theta as a x, if you will. Now, when you go to take your final, what I envision on your final is the directions will be set up the integrals required to find the area. I will not have you evaluate them. Even for a more simple one like the other ones we've done. Even for one like this, my guess is, well, it's more than a guess. The directions will be set up the integral required.
Is that because you're just going to test our integration skills on other things?
Later on in the test, I will test your integration skills. What I want to see here is you understand how to set up the area. Okay, the last thing we have to talk about. Arc length. You might remember we had a formula for arc length in rectangular form. We had a formula for arc length in parametric form. From either of those forms, you can derive the formula for arc length in polar form. The formula is, you're going to have the integral from theta 1 to theta 2 of the square root of your f of theta squared plus f prime of theta squared d theta. So it looks very much like the formula we had in polar form. You might remember, or in parametric form. The formula we had in parametric form had dy dt squared plus dx dt squared, square root of the whole thing. Kind of similar. You've got things squared, you've got a square root. You plug it in, you make it work. All right, so one of those, somebody give me a function in polar form, r equals 9. Now, I'll make it a little bit more exciting than 9.
9 tangent. 9 arc.
9 arc tangent theta. How about 9 cosine theta? Let's not go too crazy. You would have to be careful about something in something dealing with arc length. What's the thing you would have to be careful of? The graph looping around on itself. So if you had a 3 petal rose, for example, well, we don't in this case. In this case, we just have a circle, I think. 9 cosine theta. Oops, 6. We just have a circle. So when you have a circle, you can just find the total arc length and add it up. What would you have to do if you had a 3 petal rose, though? Well, what you're going to have to do is find the arc length of one petal and then triple it. There are issues with this formula when the graph loops around on itself. Same thing if you had one of the other things that we saw that had an inner loop and an outer loop. you'd have to break it into two problems. You'd have to find the arc length of the outer loop and then the arc length of the inner loop and add them together. So just be careful of things like that. All right, so if we had r equals 9 cosine theta, and what values do we want to use for theta? Theta is going to go from 0. Where do you want to end? 2 pi. Why do I want to go from 0 to 2 pi? That's all the way around the circle. I should know what the arc length is. What's the arc length all the way around the circle? Circumference. So we should get circumference is 2 pi r. What's the radius of this circle? Not 3. Not 9. What's the diameter of that circle? The diameter is 9, so the circumference, the radius is 4.5. So we should get 9 pi. We got 9 pi a lot today, didn't we? Happy coincidence. Not planned at all. All right. So our area, our formula for arc length would be the integral from 0 to 2 pi of the square root of my original function squared. So that would be 81 cosine squared theta plus the derivative squared. What's the derivative of 9 cosine? Negative 9 sine, but then when I square it, I get positive 81 sine squared theta d theta. Okay. So that's the integral from 0 to 2 pi. What's 81 cosine squared theta plus 81 sine squared theta? It's 81. Because you factor out the 81, you have cosine squared plus sine squared. Cosine squared plus sine squared is 1. So that's just 81. The square root of 81 is 9 d theta. So that's 9 theta evaluated at 0 and 2 pi. So we get 18 theta. I'm sorry, we get 18 pi. We don't get the right answer. Why not? We made a very simple mistake. Again, you got to be very careful of your bounds here. If you go 0 to 2 pi, you're going around this circle twice. So just to check, notice if I go from 0 to pi, I get the entire circle. So be careful. Don't just always think, even because it's a circle, you're going to go 0 to 2 pi. You need to be careful. This one we should have gone 0 to pi. And then we do get the right answer. We get 9 pi. All right, so watch out for that very, very common mistake, just going 0 to 2 pi. Will sometimes give you wrong answers. Questions on that?